Welcome to a lecture on Diffraction Part 1 for Bsc IVsem students in Paper 4 by Miss A.Shirly, Associate Professor and Head of the Department of Physics of V.V. Sanga's Veerashaiva College, Ballari, which is affiliated to VSK University, Ballari. We are going to study the chapter Diffraction of Light, wherein we have got various aspects of diffraction. So I have divided this study into 4 parts, and today and now we are going to study part 1. Part 1, we are going to understand diffraction, concepts of Fresnel and Fresnel diffractions, rectilinear propagation of light. The study of light ages back from 17th century, where we try to understand light and its properties, proposing various theories. And the various theories which were proposed were the first in 1637 in the corpuscular theory. Next came the rectilinear propagation of light, which is Wilbrod Snell in 1621. Then came the wave theory proposed by Huygens, and we try to understand various experiments, phenomenon in light, properties of light, right from 1629 to 1695, that is Huygens wave theory. Next we have got quantum theory, which has satisfactorily given explanation to all the properties exhibited by light. Now, the first optical device in light is the pinhole camera, where the formation of images and shadows were studied, and it is explained by the rectilinear propagation of light. Shadows were studied using wave theory, but it failed. But one point to be noted is, according to wave theory, the shadow region should not be sharp at the edges. But the careful experiments conducted by Grimaldi in 1665 have revealed that geometrical shadow of an obstacle is not very sharp, but the edge of the shadow is not sharp but contains bright and dark interference fringes. They try to explain this using interference. Now, it was thought that due to interference of direct light and the light reflected from the edge of the obstacle, the fringes were formed. But if this were true, then the shadow region must be having large area than expected according to rectilinear propagation of light. On the contrary, we have the shadow region smaller area, indicating that light bends into the region of geometrical shadow. In 1818, Fresnel gave an explanation for this phenomenon, and he named it as diffraction. So what is diffraction? Diffraction is the slight bending of light as it passes around the edge of an object. The bending of light at the edge of an obstacle, and hence its encroachment into the region of geometrical shadow, is known as diffraction of light. The amount of bending depends on the relative size of the wavelength of the light to the size of the opening or the aperture or the slit. With naked eye, we can see the bending of light if the wavelength of the light and the width of the slit or the opening are same. The best example we can find in nature is the silver lining of clouds. We can explain that bending of light or diffraction occurs around the tiny water droplets in the cloud of the atmosphere to form the silver lining at the edges of the clouds. Now, diffraction can be explained, or was explained by both by Fresnel, but in two different ways. One we call it as Fresnel diffraction, another one is Fraunhofer diffraction. And the basic distinction between these two is only the distance between the source and the screen with the obstacle or aperture. Now let us see what is Fresnel diffraction and what is Fraunhofer diffraction. By definition, Fresnel diffraction is a diffraction or bending of light which occurs when the source and the screen are at finite distance from the obstacle. However, in Fraunhofer diffraction, both the source and the screen are at infinite distance from the obstacle. In Fresnel diffraction, spherical or cylindrical wavefront falls on the obstacle. In Fraunhofer diffraction, plane wavefront falls on the obstacle. In Fresnel, no lenses are used in Fresnel diffraction to get the image on the screen, or a lens between source and the obstacle is not used in Fresnel, but converging lenses, the convex lenses, are used to study Fraunhofer diffraction. The fourth difference is waves falling on the obstacle will not be in the same phase. In Fraunhofer diffraction, waves falling on the obstacle have exactly the same phase. Now the last difference is Fresnel diffraction is general case of diffraction, which reduces to Fraunhofer case when the source and screen are at infinite distance from the obstacle. That means Fresnel become Fraunhofer diffraction when the distance between the source and the screen from the aperture or from the obstacle are infinite. Now Fresnel explained the diffraction using the following assumptions. Number one, the entire wavefront can be divided into a large number of elements, or he called them zones, Z-O-N-E-S, or small area, such that each of these elements act as a source of secondary waves, emitting waves in all directions. Means what? The wavefront is divided into zones of small areas, and each area acts as a source of secondary wave, and these waves travel in all directions. The effect at any point O will be the resultant of secondary wavelets reaching O from various elements of the main wavefront AB. Now you see, in this figure, S is a slit and there is a wavefront. Now the effect we are observing is at O. It should be, if it is, according to rectilinear propagation, it should be a sharp image at O. But we see that it is spread over the region OX. The effect at any point O will be the resultant of secondary wavelets, I said. The amplitude of disturbance at any point X due to the secondary waves from an element of the wavefront situated at P is a function of both the distances Px and the angle theta between the line Px and the normal to the wavefront PO at P. The variation of amplitude with the angle theta is represented by an obliquity factor given by 1 plus cos theta by. Now in this figure, when theta is 0, the wave move along the normal to the wavefront along PO, and hence the zone around P has maximum effect at O. But if when theta is 90, cos 90 is 0, and the effect in a direction perpendicular to the normal to the wavefront is 1/2 of the effect along the direction of wave propagation. That means it is halved. When theta is pi, cos theta is -1, and 1 plus cos theta by 2 is 0. And hence the wavefront has no effect along a direction opposite to the direction of wave normal. The failure of wave theory in explaining the absence of backward wave was accounted by this explanation. Now let us see, is it diffraction or rectilinear propagation of light by which we are going to see an effective image at O. Let us consider a plane wave ABCD propagating along x-axis towards a point O, as shown in the figure. Even though the waves emitted from different points of the wavefront with the same phase, while they reach O, they have phase differences due to the two reasons. Number one, the waves from different points travel different distances, and two, obliqueness of the wave reaching O from different parts of the wavefront has different values. Now to determine the resultant effect at O due to the entire wavefront, the following procedure is followed. Drop a perpendicular from O on the wavefront to meet it at P. Then P is known as the pole of the wavefront with respect to the point O. And let OP be equal to B. If lambda is the wavelength of the monochromatic light, then imaginary spheres are drawn with point O as center and radii having values OM1 in the figure is equal to B plus lambda by 2. Similarly, OM2, B plus lambda, OM3, B plus 3 lambda by 2, and so on. So that they cut the wavefront into concentric circle of radii PM1, PM2, PM3, and so on as. Now the areas enclosed between these circles are known as Fresnel half-period elements or half-period zones. The Fresnel zones are the annular rings in the wavefront with the waves from the corresponding points of adjacent areas differ in path by half wavelength. What are Fresnel zones? These are the annular rings in the wavefront with the waves from the corresponding points of adjacent areas differing in a path difference of half the wavelength or lambda by 2. In other words, the waves from the corresponding points of an adjacent zone reaches the point with a time delay of t by 2. The area of the first circle of radius PM1 is called as first half period zone. The areas of annular rings with the M1, M2, M2, M3, etc. are known as second, third, fourth, etc. half period. The amplitude of the wavelet at the point O depends on the following factors. The amplitude at the point O is directly proportional to the area of the zone. A is directly proportional to, small a is directly proportional to capital A of the zone. The amplitude falls off inversely as the square of the distance of the zone from the point O. There is an inverse relation with the distance of the zone from the point O. Third, the amplitude varies with the obliquity of each zone. That means angle between the normal to the wavefront and the line joining the point O to the zone. It is measured by the equation 1 plus cos theta by 2. The amplitude decreases with increase in obliquity. This decrease is extremely slow but is steady. Now let us find the area of the nth half period zone. Consider the radius of the first half period zone, that is PM1 in the figure. That is given by OM1 square minus OP square, square root of course, under square root. That is equal to B plus lambda by 2 whole square minus B square under square root. Now when we simplify it, you get it as root B lambda, neglecting lambda squared by 4 compared to the other terms. Well, the radius of the second half period zone is given by PM2 is equal to, you can simplify, you will get square root of 2B lambda. Now generally the radius of the n-1th zone can be given as PM suffix n-1 is equal to square root of n-1 B lambda. Let's call that equation 1. Now the radius of the nth zone is given by using the same relation PM suffix n is equal to square root of nb lambda. Therefore, the difference of these two will give you the area of the nth zone. Now area of the nth zone is equal to pi mn square minus pi pm n-1 square, that is pi into brackets nb lambda minus n-1 into b lambda, where we get this as pi b lambda. Let's call it as equation 3. Now equation 3 shows that the area of the nth zone is independent of the zone number. This is very important. What did we learn? The nth zone's area is independent of the zone number. The area of each and every zone is a constant, independent of the zone number. Now the radii of the zones are proportional to square root of n, even though the area of each zone is the same. Hence the width of the zone decreases from first to the outer zone. The contribution towards the amplitude of the wave at O has the same value for each and every zone. Now let us understand the distance and the obliquity factors involved. Due to the gradual increase in the distance of the zone and obliquity of zones, the amplitude of the wave received at O is of continuously decreasing values. Now let's understand it like this. If M1, M2, M3 are the amplitudes at O due to the first, second, third zones, half period zones, then M1 is greater than M2, is greater than M3, is greater than etc. etc. Mn, such that the amplitude of any zone may be taken as the arithmetic mean of the preceding and the succeeding zone. Thus, to a close approximation, we can write M2 is equal to M1 plus M2 by 2. Now, let us see phases in this way of these waves in these zones. Now, what is a phase? Phase is a condition of the wave at any instant. Now we have seen M1, M2, M3, M4, M5, and the distance of the corresponding points of successive zones all differ by lambda by 2. The waves from these zones arrive out of phase. In other words, the waves from odd zones, that means M1, M3, M5, arrive in phase from one another, and the waves from even zone arrive at another phase but are in phase within themselves. The waves from odd zones have a phase difference of pi with the even zones. Due to this, the resultant amplitude at O is written as A m1 minus m2 plus m3 minus m4, 1 and 3 plus m2 m4, like this it is written. A is equal to m1 by 2 plus m1 by 2 minus m2 plus m3 by 2 plus brackets m3 by 2 minus m4 plus m5 by 2 bracket close, etc. The expressions in the brackets are each 0 and resultant amplitude at O reduces to the following value. What is that? A is equal to m1 by 2 plus mn by 2 if mn is odd, and A is equal to m1 by 2 plus mn minus 1 by 2 minus mn if mn is even. If n is quite large, then the effect due to n minus 1, the Rnth zone is almost negligible on account of the distance and obliquity of the zone, and hence the resultant amplitude due to the whole wavefront reduces to only m1 by 2, that is 1/2 of the effect produced by the first half period zone alone. Now we know that intensity is proportional to the square of the amplitude, so I is equal to m1 square divided by 4 . Thus, this shows that a small obstacle of the size of half the area of the first half period zone is enough to stop the effect of the entire wavefront. Since B lambda is very small owing to small wavelength of light waves, a small obstacle of the size of B lambda by 2 is sufficient to produce zero illumination at O, and hence the obstacle of that size produces shadow. Now, the rectilinear propagation of light is explained using diffraction. And this is how it is explained. On the other hand, if the size of the obstacle is less than the half of the area of the first half period zone, the intensity of the light at O is not zero, and hence the light bends and enters into the region of shadow of the obstacle, and hence the point of O is illuminated, which explains the diffraction of light observed at the edges of obstacles or apertures.